Hello, and welcome to the Chapter 8.2 online learning video on solving homogeneous linear systems. So we saw in the previous chapter that a fundamental solution set to this system of differential equations, which corresponds to the matrix equation x prime equals ax, where a is this matrix corresponding to the coefficients, was x1 equals that and x2 equals that. And we saw that therefore the general solution is an arbitrary linear combination of these. And in as much as x is just shorthand for yu, this is the same as saying that the general solution is this, writing out what x1 and x2 are. And then one can distribute and equate the first element here with the first row here. And one gets that y is c1 times 2e to the negative t plus c2 e to the 5t, that first line, and likewise with what u is. So this and that are equivalent. Now, what we're interested in this section is how do we find such solutions in the first place? Well, notice that these two solutions, x1, for example, we can pull out the e to the negative t, since it's a scalar that affects both components, and likewise in x2, we can pull out the e to the 5t. So both of these are of the form k times e to the lambda t. Here lambda would be -1, there lambda is 5, and it's some vector in front of it. And what we want to find is, given a matrix equation, x prime equals ax, what are k and lambda that's satisfied as solutions? So what we'll do is we'll take our k e to the lambda t and plug it into x prime equals ax and try to find what k and lambda are. First, when we plug into the left-hand side here, then we're taking the derivative of k e to the lambda t, and that derivative is going to be lambda k e to the lambda t. All that happens when we take the derivative, remember, for example, the derivative of this is we take the derivative of each component, and that just amounts to pulling down that constant in the exponent. So all that happens is that lambda up there gets pulled down, and we can think of it as being scaled on the outside since it affects all components equally. So that's why the derivative of k e to the lambda t is lambda k e to the lambda t. So when we plug in k e to the lambda t into x prime equals ax, that's the left-hand side, the derivative of it, and the right-hand side is ax, which is a times k e to the lambda t. Okay, but now e to the lambda t is not 0, so we can divide both sides by it. And we get that lambda k equals ak. So rewriting that, ak is lambda k, and k is just our name for it. We may as well call it v if this looks more familiar. It's av is lambda v. It means that k is an eigenvector of a, and lambda is the corresponding eigenvalue. So if we can find eigenvalues and eigenvectors of a, then we can generate solutions of the form k e to the lambda t, and then take arbitrary linear combinations of them and get all solutions, provided that we have a large enough set of solutions generated in this form, i.e., provided that we get a fundamental solution set, n linearly independent solutions for an nth order or a system of n linear homogeneous differential equations. So that's what this theorem is. If lambda 1 to lambda n are n distinct real eigenvalues of the coefficient matrix A, where A is n by n, i.e. it corresponds or comes from a system of n linear homogeneous differential equations that are first order. Remember that each row of the matrix corresponds to one equation, so when we say that the matrix is n by n, that just means that it corresponds to n equations. But provided that that's the case, then that means that we will have n distinct eigenvector eigenvalue pairs, and therefore a fundamental solution set will have n linearly independent solutions to a system of n differential equations, and therefore the general solution will be an arbitrary linear combination of them. This is our cx1 plus c2x2 plus so on out to cnxn. And fortunately, we learned how to find eigenvalues and eigenvectors of matrices. That was the point of the Chapter 8 preliminary lecture. We know that lambda is an eigenvalue of A, if and only if the determinant of A minus lambda I is 0. And then if lambda is an eigenvalue, then a corresponding eigenvector satisfies A minus lambda IV equals 0. So for example, let's solve this system of linear differential equations using this. So this corresponds to yu prime is 2 minus 2, 10 minus 7 times yu. That is our x prime equals ax. So what we want to find is first, what are the eigenvalues? Well, the eigenvalues are the lambda that satisfy determinant of A minus lambda I equals 0. Writing out it saying that, which is saying that the determinant of this matrix equals 0. And the determinant of a 2 by 2 is just the main diagonal minus the other, as I've written up here, and as we saw in the chapter 8 preliminary. So that is 2 minus lambda times minus 7 minus lambda minus negative 2 times 10. And we want that to be equal to 0. We FOIL out, and then we simplify and factor. And we get that lambda is negative 2 and negative 3 are the eigenvalues. And then for each of these, we need to find a corresponding eigenvector. So we found the eigenvalues are negative 2 and negative 3. First, let's find an eigenvector for lambda equals negative 2. That means that we want A minus lambda I v to be 0. Here we're doing it for lambda is negative 2. So we want to find a v that satisfies this equation. And yes, we can always row reduce for what we learned in the chapter 8 preliminary. But if we can eyeball, then that saves us time and all the better. So can we think of numbers to put here and here so that when we sprinkle down and add, then we wind up with 0 and 0? Take a moment and think about that. If you saw that, yes, the first column looks like it's double the second column, but with a minus, then that's right. And that means that if we put 1 and 2, then when we sprinkle down, i.e. multiply and add, then it works. Each of these rows adds to 0. So v equals 1, 2 works and is thus an eigenvector for the eigenvalue negative 2. So we found an eigenvector for negative 2, and now let's find an eigenvector for the other eigenvalue of negative 3. So writing out it's that, and then simplifying, we want to find a v that satisfies that. So try your hand at seeing if you can find a v that satisfies that by inspection. What numbers can we put there and there so that when we sprinkle down, multiply, and add, then we end up with 0 for both rows? A good strategy is to look for the least common multiple. So 5 and 2, least common multiple is 10. So if we can get both of those to be 10 via an appropriate multiplication, then we can get them to go away via some kind of addition. So it looks like 2 and 5 work in the sense that if we do that multiplication and addition, then indeed both rows become 0. So v equals 2, 5 works and is an eigenvector for the eigenvalue negative 3. So we have found the eigenvalue-eigenvector pairs of lambda equals negative 2 with eigenvector 1, 2, and the eigenvalue negative 3 with an eigenvector of 2, 5. So the general solution by our theorem is thus an arbitrary linear combination of this k1 e to the lambda 1t and k2 e to the lambda 2t. Writing out that c1 1, 2 e to the negative 2t plus c2 2, 5 e to the negative 3t. That's one perfectly fine way to express it. And in as much as x is yu, and in as much as we can distribute the c1 inside of both of these, and likewise with this scalar, it's the same as 1 times C1 e to the negative 2t plus 2C2 e to the negative 3t, looking at the first row here. And the second row is 2C1 e to the negative 2t plus 5C2 e to the negative 3t. Which leads to another way of expressing the same general solution, that the first row, which is y, is that, and the second row, which is u, is that. Either of those is fine, and the input will be depending upon what the homework wants. It will typically in 8.2 want this kind of input. So that's quite slick and much faster than using Laplace transforms, and also more general in the sense that Laplace transforms, if you have a system of 3 equations in 3 unknown functions, then the Laplace transform becomes just a nightmare because it might involve the cubic formula, for example, and then it can be downright unsolvable in the case of systems of many differential equations. But finding eigenvalues and eigenvectors would suffice in all of those cases, where there are n-distinct eigenvalues for an n by n matrix. So, for example, solving this system with Laplace transforms would be awful, but we can find the eigenvalues and eigenvectors for it, like we did in the Chapter 8 preliminary. So this system is the same as x prime is this matrix times x, just looking at the coefficients. So first we want to find the eigenvalues of this, and that means plugging into determinant of a minus lambda I equals 0. So determinant of a minus lambda I is that. The lambda distributes, and then the subtraction just subtracts lambda from each element with a diagonal. And then one can compute that using the determinant of a 3x3 formula like we did, and get this. We did this exact problem back in Chapter 8 preliminary, if you want to go back and look at that with how we do it for a 3x3. So therefore we have eigenvalues of -3, -4, and 5. And then for each of these, we find the corresponding eigenvector. And in fact, we dealt with this exact matrix in the Chapter 8 preliminaries lecture. If you want to go back and have a look at that, you're very welcome to. We found the eigenvectors corresponding to these eigenvalues back then. And in that lecture, we found that the eigenvalue-eigenvector pairs were the following. Lambda equals -3 had an eigenvector of 1, 0, 1. -4 had an eigenvector of 10, -1, 1. And 5 had an eigenvector of 1, 8, 1. So our general solution to that system of differential equations is therefore C1 K1 e to the lambda t plus C2 K2 e to the lambda 2t plus C3 K3 e to the lambda 3t. And this is generally how we'll express solutions. But again, any solution expressed like this can be re-expressed in terms of the actual functions by just reading off the rows after we combine them together, in the same way that this is equivalent to that. Now I just want to show you what your homework for this section looks like, and with regard to inputting. So it might give you a system of differential equations like this. You need to find the eigenvalues. And then for the eigenvectors, how do you input a vector? It wants you to input it with these angle brackets, as they're called. And you can find that by going to vectors here, and then right there are the angle brackets. So then you could type -1, 1, and just click out, and that is the input that it wants. So what that means is this is the first row of the vector, that's the second row. And then for inputting general solutions, then it wants it in this form. So this is just how you type in vectors. So our C1, K1, e to the lambda 1t plus C2, K2, e to the lambda 2t. And likewise, if it's a system of three differential equations, like the one that we just saw, then your eigenvectors will have three elements in them, and it's no different in principle how you type them. Use that vector function there, and you can input the vector 1, 0, 0, or whatever it is. So on homework, you would input this as C1, and then those angle brackets 1, 0, 1 with commas, then e to the negative 3t plus C2 angle brackets 10, negative 1, 1, etc. All right, that does conclude chapter 8.2 on our very slick tool to solve systems of linear differential equations using linear algebra. Have a great one.